welcome to my talk, Bits and Pieces. So I will talk about how you can tackle a new domain, and for me about one of my hobby projects, building a telecom codec. So I work in the telecom industry at a company called Working Group 2, and we develop a mobile network core and provide it as a service. And my team maintains and operates this edge router written in Erlang and connecting to other telephone networks. So the agenda first, I will talk a bit about my problem domain, then how you can inspect data and binaries, arbitrary data, and then why the Beam is especially good at this, and finally a bit about my open source project. So say you want to build a core network. Then you can start with a mobile device, and that is usually a phone, but it can be a pager or a computer with SIM card or a modem or whatever. It connects to some antenna, and in a radio network you usually have a lot of antennas because an antenna only goes so far geographically. So you have a bunch of antennas, so you need in your core network a node to keep track of all the antennas and the devices where they are, which antenna they are connected to. But you might also need a node for blocking unauthorized devices. And then you also add a node for keeping track on the location where which devices are connected to which node and so on, so addressing database, so that you're able to route traffic to those devices later on. You might also want some database for storing text messages before they can be delivered to other phones. And you might also want to make phone calls, so route out traffic to other telephone networks. But you also want 3G to be able to connect to internet too. So then you need a node for keeping track of those antennas and those devices, and also a gateway for connecting to the internet. But you have heard of 4G, and it's a complete new architecture, so you keep adding nodes for that, new data formats, you need a new database for that. You might add some new functionality for policy control, for instance. And there's also a new node for connecting to the internet there, so you want that behavior as well. And then somewhere on the internet you find this beautiful chart, and you go, my eyes, my eyes! Of all the nodes you haven't yet discovered and implemented. And so it's a beautiful chart made by Miniake Ogawa, I'm not sure I'm pronouncing it correctly, where he listed all the different 3GPP nodes in the core network from 2G, 3G, 4G, 5G, which protocols they are talking and how they are all connected to each other. And to not have all these nodes have configuration for how they should send traffic and connect to all kinds of services and whatnot. The solution to that problem is to add yet another node, a router in between your services, in between different networks. So simplified, really dumbed down, router moves data from one socket and outputs it on another socket in some intelligent way based on addresses in these protocols that are packets that are being sent. And depending on which layer your router operates on, you might need to decode those packets in different many layers. So what network engineers know about is this great tool called Wireshark. And it can listen to your network interfaces and on streaming data traffic, but it can also nowadays open plethora of different files, from image files to whatever kind of file. And usually it's built up from these three main panes. So you have the list pane, which lists all the packets in the network capture. You have the details pane showing how each package is built up. When the OSI model is applied, it's describing all the OSI layer in the packets. And you have the bytes pane showing the hexadecimal representation of the packets, the bytes actually being sent. And these network streams can also be saved as packet capture files to your computer. And independently if it's capture file, PCAP for short, or any arbitrary file, it usually starts with some file signature of magic numbers that describes for the program reading that file how it should interpret the data. And in the file header for this PCAP format, you have the link type down there, telling how all the packets in this file, which type of packets it is. So it's Ethernet packets coming out of this file header. And the packets are just, the rest of the file is packages in a list of packages. With some meta information and then the actual packet payload. So you can go to the Ethernet specification and it will tell you how to interpret a payload. And it also have a header containing some destination address, some source address, and then a type describing what is being carried in that Ethernet frame. And here we have IPv4. And you can continue into the IPv4 specification, and you start seeing a pattern where you usually in the header have a field containing what information is being carried in the payload. So you can continue and decode all these packages until you get to the application layer. And then in this arbitrary PCAP file I found and decoded here, the application was in H248 format. I've never heard of it, so I don't know anything about it. But in the specification, they actually have specified this ASN1 format for the data, the fields in the data. And here is where OTP starts to shine, because in telecom we have a lot of specification carrying ASM1 representation of the specification, and then we can just use the ASM1 compiler directly. So the Beam, great for telecom because of all the built-in libraries that we can use. Something else that is great with the Beam languages are pattern matching, of course. Everyone says this, but it's really true, and binary pattern matching as well. And here I just wanted to show that when matching, you should really use whatever the format from the spec that has the meaning. So use that when you match and branch out. If it says A1, B2, C3, D4 in the spec, use that directly. It will make sense when you come back to the code. It's searchable in the specification, so you can find the correct part very quick. Something else that many of the languages has is this conversion between decimal integer representations, binary integer representation, and hexadecimal integer representation. Not all languages has it, I think, but Beam has it. Many others do as well. And with regard to binaries, you don't have to work on byte boundaries. So if you have a 32-bit integer number, use that if that makes sense. If you only want to match on a certain bit, then match on only a certain bit. You don't have to allocate the full byte and manipulate the full byte of data. Variables are bound from left to right. So usually in protocols, as the examples I showed, you have some fields containing a length of the payload in the packet. So we can bind that length and then right after match it out in the function header, for instance, and start working on this chunk value, for instance. Macros, great for making sense of magic numbers, giving meaning to arbitrary numbers. A 7 in this context, if I were to come back and look at code with just a 7, I wouldn't understand why it's a 7 and not a 6 or a 5. But given the names, we can all understand this format better, I think. And finally, so what I've done is I've written a codec for a lot of different telecom protocols, so you don't have to go in and look at these 3GPP specs. So this is my contribution back to the open source community. And I try to implement as many of the different telecom protocols that I need in my work or just fancy. I'm a bit weird, I like those specifications. Yeah, and my goal is to have a unified decoded format for human readable format for all the supported telecom protocols. So finally, all domains have its its own domain languages, and I feel that it can often, coming into it, can often feel cumbersome and overwhelming, but just remember to everything can be broken down into pieces. And most bits have meaning. And remember to have fun on the way. As I think Quinn said it in the morning sessions. Yeah, thank you.